Thanks everyone for joining. I also want to introduce someone that won't be speaking today, Ashley Francis. You can see here with me on the screen. Ashley from LJA Engineering actually was the engineer who worked on the case study that I'll be showing. So again, this is a case study, preliminary case study, work in progress. We'll kind of show where we've gotten to date. So for those of you who perhaps don't know, I guess, who XP Solutions is and what we do, in short, we are a group that provides original, high-performing software solutions. My role in the past has been kind of heading the client services side of our group, and we have 4 offices kind of scattered around the globe. So you can think of how our support group can really be accessed kind of around the clock, which is something that I think is quite beneficial. So let's move into what I'm going to be talking about today. So I'm going to end with looking at the clear visualized case study that Ashley Francis and myself put some time into. Before we start looking at the case study itself, we're going to start with just what is a conventional green infrastructure design process. Some everyday mistakes that we might find. Unfortunately, those might be occurring, closer to every day than we would like. Move into what I'm going to call design tenants to avoid some of these issues, and then, of course, move into that case study. So before we do anything else, what are we talking about? So I'm going to use the term green infrastructure, low impact development. There is a whole range of these terms that are used across the U.S. and across, I guess, international lines all over the world. Lots of different terms. Green infrastructure and low impact development are the ones I'm probably going to use. These are all talking about the greater practice of sustainable drainage, holistic stormwater planning. So green infrastructure is kind of this greater approach to holistic drainage design, whereas the individual facilities, so you can see here on the right, an individual swale or an individual rain garden, I'm going to refer to as a stormwater control. That's kind of the individual items that make up this greater plan. Okay, just so as no one's lost, that's what I'm referring to. So what is the conventional green infrastructure design workflow, if you will? So we are going to incorporate green infrastructure. We're going to start out with this holistic approach to runoff drainage because we're trying to address water quality. Okay, that's the assumption we're making. But we actually often approach this from a pretty simplistic point of view. So we don't often try to assess or analyze the true pollutant concentrations, pretty complex stuff in our runoff from our site. But we make a couple assumptions so that we can purely have a volume-focused plan. So traditionally we're going to start with looking at what is the rainfall or hydrology on our site. So we're going to have that first flush, we might call it, or the water quality event, if you will, looking at, depending on your area, around 1 inch, maybe a little bit more, maybe a little bit less, but that first inch of runoff volume, we're assuming is going to carry with it the vast majority of pollutants. So think of it has been all summer long, it hasn't rained for, let's say, 4 months, maybe more. This past year out here in Portland, Oregon, where we're located, hasn't rained for 4 months, and the first time it rains an inch. That 1 inch of volume is going to carry with it much of the pollutants that can be, I guess, removed from the site that will wash off. So we need to, first thing would be treat that volume. Okay. So again, the actual pollutant concentrations often are ignored. Okay. So how do we deal with, I guess, the runoff from a site? Well, the first thing is we size our individual facilities and ultimately our entire treatment train to handle, to retain that water quality volume event, that first inch of runoff. our treatment train needs to fully contain and infiltrate or treat that volume. Okay, well that 1 inch event, well that often isn't even I guess the 2-year storm. It might even be less than that. So we're going to treat and retain and infiltrate that more minor event, that water quality volume. But then we still need to design, I guess, safe flow and appropriate drainage across our site for the higher flooding events, so the 2 through 100-year more flood events. So we're going to start to reiterate our size for our water quality storm, and then size our facilities, our drainage paths, the outfalls for kind of the typical progression of the larger storm events. These calculations, this design is most often done with a rational method, Manning's equation, or equations kind of along that line. The point here I want to make is many different spreadsheets and tools end up getting used. So I said 5 or more. I've personally worked on projects where I have used over 8 different tools to look at everything from the water quality, event, volume sizing, outfall, orifice sizing tools and spreadsheets, and then let's look at swale capacity, flow capacity. You end up getting all these tools that are coming together for this project. So that's the kind of conventional way that we do design. So I want to ask everyone a question. There's going to be a poll. I want to get everyone's answer on this. So here's kind of a longer question. Okay, so now that we know kind of what that design process is, that probably most of the country, almost everyone probably follows that. So with that being the process, have you ever seen or reviewed a drainage plan where perhaps the required facilities or the calculated facilities are too big for the site? Perhaps a swale is needed, but hey, it needs to be longer than there actually is room on the site to hold it. Have you ever seen a plan where to implement it, it would actually require the drainage to move uphill because the levels weren't part of the analysis? Where perhaps the outlet is set at a higher level than the maximum possible water level in a stormwater control or a pond, let's say. All right, so instead of being able to spill out of the outfall you've designed, the water actually would probably drain over the banks first. Or perhaps the scariest one for myself would be where there's a critical mistake in the drainage plan that was discovered, I guess, after it was reviewed and approved by the client or city. So these ideas, I just kind of want to get everyone to check. Have you seen this? All the time? Well, that's scary, but might be a possibility. Rarely, occasionally, or I have never seen this before. I think I personally would be much more on the frequently side, which is a bit scary to put that, but that's where I would certainly be. So I'll share the results. So you can see, occasionally, a few people might have said, never seen that. I would love to work with you. Sounds like that's a great place to be. Occasionally, frequently, that's certainly kind of what I would say I have seen of, groups I've worked with, groups I've spoken with and done trainings for. This happens. It's pretty terrifying, but it happens. Okay, so this is what I'm talking about, these kind of everyday mistakes. This happens occasionally. This will happen on projects. So following this conventional workflow, we end up seeing much more than we ever would want to. Plans where water can run uphill, where we have the treatment system be bigger than I can actually fit on my site. A really common one, I think, is elevations and outfall structures don't line up. Okay, that sinks the ship all the time. So I imagine it sounds like everyone has seen these before. I guess the question is, right, how can this happen? how can any of these issues occur? Last I checked, I myself is a licensed professional engineer with a stamp to prove it. I imagine many of you are. Everyone works on teams where you are a licensed professional. How can we, size facilities where we have to force the water to run, upstream to work? Okay, so how could we not see our designs as being wrong? That's the question. How can we not see this? So that, I think, is really the point of this, is we just can't clearly understand or communicate how our stormwater systems will behave. So we're looking at the fact that the conventional drainage process, so this planning process, really works against having clear communication. The project I worked on, where I personally had 8 or more different tools, not even putting that into a report, but understanding all the components myself is difficult. Okay, so this is the idea of it's very difficult to even self-review work, much less get this into a competent report and have someone else review, be it your boss, be it your city or client. Okay. And the scariest thing is, what if no one finds your mistakes? That doesn't mean you're not wrong. It doesn't mean that when it gets built or during construction there won't be issues. So that ends up being a real sticky point there. So what if no one finds it and it's only after things are constructed or during construction? That is a big issue. So the item here is just that clearly understanding and communicating the functionality of our often complex drainage systems, I'm going to say, is one of the single most impactful components of our design process. So being able to communicate what we've done and understand our own work. So be it explaining to your manager, like I said, how your design will work. Perhaps even better is saying why it won't. Okay. Maybe a reviewer at the city or at a county who is trying to approve a project, but the ease of the communication surrounding that drainage plan is causing a problem. So I'm going to say the statement of the ease of the communication surrounding the drainage plan defines the success of that plan. So how easily and readily we can communicate and understand a drainage plan, this inherently is going to follow how successful that plan will be. So with these kind of bigger ideas in mind, I have put forward a couple design tenets, I'm going to call them. So if we can follow in our practice kind of a workflow which checks the boxes of these design tenets, we're going to have just inherently better, more competent design, and designs which are not going to run into perhaps what would seem very easy to avoid and looks like very common issues. So these design tenets all fit under the umbrella that the drainage on your site is going to dictate or influence all other project aspects. Okay, so the first is always work on live project data. My example of my real world, I'm not going to name names of what project that was, but the real world scenario where I had 8 different tools just for my drainage plan. There is no hope of using spreadsheets and hand calculations working against live project data the way that I needed to. Okay, so we always have to be able to work against, review, and lay out against live project data, CAD, GIS, what have you. So this is one, we need to communicate the drainage plan instantly to anyone who would be a stakeholder. That might seem at first, cumbersome to say the least, if not impossible. But it's something we have to do. We have to be able to, on a daily basis, push where we are in our kind of rough draft site plan, a rough draft drainage plan to the site team. Okay. Same as we're getting their live data, they need to see our live work in progress to see, and maybe they'll identify something, maybe there's some sort of utility access that I'm not thinking about. I'm trying to put in a swale or a rain garden. Well, there's utility access there that I'm not thinking of. Well, that's going to be a problem. Okay. communicating just between the design teams, and ultimately communicating to, managers, clients at a moment's notice, is one of the ways that we have to position our workflow. So we have to, I guess this one is sell yourself, sell your solution. Okay, it might sound a bit odd, but it is so important, okay, as far as from consultants to sell what you're doing, to sell your competency of your engineering group and the competency of your designs to your clients. Well, as a more junior engineer, it's very important to sell the competency of your work to your manager. So I mentioned before, the most important thing is getting a successful design to work. To me, an immediate second is identifying as early as possible when a design won't work. Okay, so if you can, let's say as a junior engineer, explain to your manager how and why something won't work a week before, right, you might have otherwise, you're going to look pretty good, and that's going to save you a lot of headaches down the road as a team. So one thing we also can't do, we can't ignore complexity. So again, this is a design tenet. We can't ignore complexity. We can't not try to represent or assess what's actually going to be on our site. Often because of the tools we're using, right? Hey, my spreadsheet orifice sizing tool just isn't robust enough to look at the combination of orifices and weirs and kind of side flow systems for high flow bypass. Well, that's not good enough. We have to model what's going to be out there in the real world. I'll follow that up with, we have to, seriously, really, we always have to assess what's being proposed. Okay, if we can represent exactly what's going to be put in the ground, make sure it works, and communicate that it's going to work, well, our margin of success is greatly improved. So we're going to touch on get into the case study here in a second, but we'll look at the workflow we use with XPDRAINAGE, the workflow that we'd use with this case study. So the first would be we started kind of with that pre-developed or kind of the rainfall runoff part of the assessment. So we're going to start with looking at the water quality volume, calculating what that's going to be, looking at the runoff from the site. Again, with XPDRAINAGE, we can absolutely get into the pollutant wash-off concentrations, what have you. A lot of groups don't do that. Okay, we can have a whole other series of webinars on how and why we should, or how it's okay that we don't. But we can absolutely assess that using XPDRAINAGE. You'll see in this case study, we happen to not do that. So we begin to have our volumes that we need to infiltrate and retain. We have our the runoff rates in these higher flooding events. Well, we would begin to start with some, as you'll see in the case study, perhaps some initial pipe sizing. Okay, let's look at just some quick estimates on the size of facilities, flow controls. So we have just in a few minutes an idea of the scope of which we're working on. And then we begin to connect our treatment train together, add in individual stormwater controls, perhaps have together our entire treatment train. And ultimately, perhaps the most important is clearly define the existing conditions and the developed condition rates and volumes. So we need to compare concretely that we are reducing the volume appropriately to our existing conditions, or fully retaining and infiltrating that water quality volume. So having a clear comparison is a very, very important part. Ultimately, one item that is easy to overlook, or perhaps more convenient to overlook, is the modify. Hey, how you plan. The first pass of your design didn't quite work. Let's go back and make some modifications. If we were to look at a timeline, this modify, compare, alter your site to optimize it is the vast majority of the time in the design process. So making that feedback loop and having that process be as minimal as possible, right, is kind of what we're going to focus on with XPDRAINAGE. So let's look at our case study. So this happens to be a master planned community LJA Engineering is working on. So this was Ashley Francis, who I spoke about previously. To give you a sense of where in the world this is, this happens to be in Montgomery, Texas. The total project site kind of outlined, it's like kind of the yellow portion of that map. Our kind of phase one, if you will, portion is only about 160 acres. Okay, so pretty good size. This is a pretty significant master plan community that integrates this master plan development along, a significant golf course. So that's kind of the very big picture, what we're looking at here with this preliminary case study. So what was the purpose? So this case, we had a very specific purpose, and it was to develop and improve a residential site with no adverse hydrological impacts. But I guess what I want to add here is the more subtle purpose is we want to show, right, this is the general plan that you would use on any drainage site. You want to improve the site, pave a lot more area, but not have any adverse ecological impacts. We're also in this study proving to a developer that green infrastructure and holistic drainage design is worthwhile, that it's going to save money, make for a much more attractive development, and really increase the worth of the site in the number of ways. Okay. So we're going to look at mitigating, in particular, as far as the drainage goes, the 25 and 100-year ARI events. So this area in Houston, if you're not from the Houston area or not from Texas, don't know, right, this area gets a very, very significant amount of rain. Okay, so if I remember correctly, we're looking at 12 or more inches of rain for the 100-year event. And a lot of people could probably argue that that might need to be increased with the rain over the last decade down there. But so we're looking at, in particular, mitigating the discharge from our site in these higher flooding events, as well as treating as well as treating that water quality storm event. Okay. So what we'd like to find is if we can incorporate some green infrastructure, as well as begin to get a big improvement in the quality of water running off our site, but ultimately we can reduce the very, very, very large detention facility, which is kind of the standard way to approach drainage in this area. So typically it'd be just a giant end-of-line detention basin. We're looking at, since we would plan for a kind of holistic, distributed green infrastructure system, well, that's going to reduce the size and necessity of some of that detention basin. As I said before, assess the viability of green infrastructure when compared to the well-known traditional drainage approach. So first, what was the methodology in really convincing at every step of the way a developer, a client, that green infrastructure is worthwhile? Okay, so the very first thing we did was a preliminary flow assessment. So we looked at the rational method. Let's just, in a very short amount of time, get a sense of what kind of runoff we're going to get from our site and do a pipe sizing assessment. So right away, with a couple hours of work, have an existing and developed pipe sizing assessment, okay, a very short amount of time. So by showing, I guess, a client that there's potential for some significant cost savings just purely in the size of pipes you're going to need to purchase. So that was an early, very early green light on this project of, yep, that looks promising, let's keep moving. So what would we do next? So we would say, let's set up our more detailed existing runoff plan. Since we're going to try to convince someone, well, really convince ourselves, between a traditional typical drainage plan and a green plan, we're going to do both. So we're going to have our existing runoff plan and then have our traditional drainage and our LID-based plans. So let's just look for a second at what we did in the in the rational assessment and pipe sizing. So we looked at runoff coefficient and time of concentration were things we could adjust. So we have our developed site, okay, as you'd expect, and we made an effective green scenario to assess. So for that effective green scenario, we took the traditional developed runoff coefficients and time of concentrations and ended up kind of adjusting those. So you would decrease the C value a bit to represent the incorporation of green infrastructure, as well as increase that time of concentration. So we have distributed green infrastructure collecting all the water. We're going to effectively have a little greener site, so a lower C value and a little longer time to get downstream. So with this, again, this was kind of a very early assessment. With these two developed and green scenarios, we looked at pipe sizing. So let's just size the whole system based on the rational flows and Manning's equation. Pretty quickly we could show that there's a good sized reduction in pipes along both what I'll show you is kind of the main trunk line of the system as well as the lateral branches of this drainage system. So you can see here in this plan view on the right, there's a kind of a dark purple trunk line, I'll call it, which kind of the main flow through the site. And then the lateral in kind of a lighter purple. So all that is just kind of sized in one pass. There were, I believe we also looked at, minimum cover. I'm not going to get into the details of, all of the different types of pipe sizing we could get into. I'm going to stick to kind of just what was done for this case study. But I believe we looked at, give us some pipe sizes with the pipes we had available in that area, and make sure we don't have, a certain minimum cover depth was what we used. And ultimately we get, the flow rates, the capacity, what have you, for that system and the associated pipe sizes. Okay, so from there, okay, we got a very early green light. Yeah, this looks promising. Let's keep moving forward. So we look at the kind of existing runoff plan. What I'm showing in the screen now is what we would call deluge. So we deluge the site. So apply a little bit of rainfall to the site. And it's a very quick, 1 second long calculation of 2D surface flow. So if anyone's heard of 2D modeling, that is often a much more robust, takes much longer to run. This is a more simplistic 2D assessment. So with this quick 2D assessment, we get a sense for the overland flow paths and really can delineate our catchments based on that and place and plan how our site should incorporate green infrastructure. So we defined the catchments based on this information and began to get an idea of where in the developed scenario we could start placing our facilities. So let me set up what the typical traditional drainage plan would look like. So based on our rational sized pipe network, we have all of these catchments, right, collected into a storm sewer pipe system, and that dumps out into the bottom portion of the site into a giant pond. Something to notice, there's a kind of a western valley on the left-hand side of the site in that light purple. Well, there's kind of an untreated valley. So it's going to stay green, right? But there are going to be some changes to land use to that area. So we would need to kind of overcompensate in our detention basin because we have kind of an untreated, directly draining off our site, kind of valley. So what would we need for this detention basin, being really our sole attenuation facility on this site? So we would look at having a pond, almost 7 acres, with 2 outfall pipes. I believe those were, so 2 outfall pipes and a high flow weir. Just to give a sense of what we're looking at here, we have in this long section, you can see all the pipes running downstream. Everything dumps into the pond. The pond fills up and really what I'll touch on later is this pond is kind of at the point of flooding. The pond is full to the brim, okay, in this scenario, and we're almost at 7 acres. So this is our plan. So let's look at that kind of green, if you will, the green approach. So how could we incorporate green infrastructure across this site? Now, because this was such a preliminary assessment, we didn't get into the detail that we certainly could have and would if we spent any more time. This was supposed to be a very quick, it was intended to be a very quick study. So we looked at having lumped rain gardens for each neighborhood. So each catchment is just going to have one rain garden. In reality, each catchment will probably have half a dozen or more rain garden facilities distributed across that smaller site footprint. But for this, we just want to look at, okay, what would be the total size we need, and give or take, that's a pretty good approximation. We would just chop up that area and move it around. So for this type of preliminary study, that's what we went into. So lumped rain gardens for each catchment. You can see here on the right is a rain garden or bioretention system. That's what we put on the site. And there's a bit of a workflow that kind of guides you through laying this out. We had a surface that we were using, and so because of the surface and because of the background information, we just simply drew our facility, and all the information you see on this dimensions screen, so this dimensions tab, is automatically updated for us. So I just simply drew kind of where I wanted it to go, how big I think it should be, and automatically that's set for us. So right away we can see, based on the top area of how I've drawn it, I'm assuming a 1 to 2 slope. So all of the dimensions of the facility were automatically applied for me. I could then adjust either through editing the numbers or just dragging and moving and expanding the shape of this rain garden. By adjusting the shape in the plan view, it adjusts all these numbers for me. So that was pretty convenient. By default, we had probably a pretty common sub media, so the filter media here, and automatically connecting these facilities up. Inlets and outlets were automatically set up for us. We can get into detail where we need to on having specific outfall structures. If I need to have a specific orifice that controls the flow, or a multiple facility. Maybe I have an orifice for a minor event, an orifice for a higher event, and then a weir, all kind of in one vault. Well, that's actually what I'm showing here. I had a kind of a multiple control facility. Okay, so that's all put together for us pretty easily. The advanced, advanced really being different ways you can have infiltration occur, what have you, into the natural soil in the area, pollution. We didn't get into that for this site. Okay, so we really just had the dimensions, which were, almost completely automated for us, and I just used the same filter media depths and layers everywhere. So you just threw these together. We can see a big picture of how the drainage system looks. Okay, we have ultimately everything drained to the pond, but before it gets to the pond, within each catchment, there's a rain garden and there's treatment. There's still that untreated portion of the site, okay, leaving on the left side. Here's a close-up view of what we were looking at. So we were representing, again, don't ignore complexity. We were representing, even with this lumped facility, the fact that we have flow into this rain garden, but we also have a high flow bypass. Okay, so a lot of these facilities, it's a sandbox. All right, you can't just turn the fire hose on the sandbox, have the 100-year event rush through. You're going to scour your facility away. Okay, so you have your minor events move through that facility and have a high flow bypass. That's what we're representing here. You can see in the plan view there's a kind of a dotted line showing where that overland flow path would be. The solid line is our pipe. Okay. So with this incorporating this green infrastructure. We looked at a little over an acre smaller size of that pond, only a single outfall pipe, and no freeboard issues. Okay, so pretty significant difference across this site. You can see here's kind of a cascade from one of our rain gardens down into the pond, and then through the end of our trunk system. So perhaps the most important part, what was learned? Okay, what are the next steps? I often call what this case study was as a detailed schematic design. Okay, kind of a misnomer. But again, this was a very preliminary assessment that was looked at. This is kind of a first pass on proving if this would work, proving in this area, for this type of client, if green infrastructure would make the kind of improvements that would be desired. And sure enough, it did. So now that we really see that, great, this can work in this area, this would work for this client, this group, we could get more detailed. But for the scope of this work, it was very preliminary, and the focus was to take very little time to do it. So next steps, well, if we were to continue on this process, well, it would be a refinement of that green scenario, and perhaps a little more time in the traditional drainage scenario. We had that giant detention pond. Well, it really wasn't quite working as we needed it to. It was full to the brim. The freeboard was completely exceeded. So we probably would have needed to make that main pond bigger, maybe adjust some pipe sizes. The green scenario, certainly, we could refine that further, optimize that. I think our pond could still be reduced. Some facilities, maybe some rain gardens increased, some decreased. One big one is we only looked at rain gardens. We only looked at a bioretention system for these areas. But as you've probably seen before, there's a number of different types of facilities that we can incorporate, even just aesthetically, into this, the edges of this golf course. We could have, what I'd call dry swales, where you have essentially a bioretention, right? So some sort of sand filter media at the base of a swale, so it can infiltrate and hold on to that minor event. But for a higher event, perhaps it can store and very slowly transport and attenuate a higher event. Okay, so all sorts of different types of swales and rain gardens, and reuse, honestly, could have been looked at on the site. So as far as Ashley, again, I'm speaking for Ashley in this. This was part of our presentation that was done in both SESWA, which was in the Southeast, as well as EPA 6 regional conferences back in October. Okay, that's kind of where a lot of this work was showcased so far. So Ashley's comments is really the drag and drop nature of the drainage and LID elements, especially in this type of assessment, saved heaps of time. So being able to have just a couple background items and based on that, draw the items we want, move them around, and have the levels automatically updated, have the size of our facilities updated and modified based on how we modified something in a plan view. A huge time saver. The other being that, I think I already touched on it, but the automation of the elevation data, right? That, for me, was always the biggest pain on a project, working on tools, having the final elevation be what I'm representing to be able to put on the plans. In this case, this was preliminary, but we could have easily had the work be finalized, by the development plan be finalized, and just import a new surface, and automatically levels will be updated. Okay, so all of that kind of work, which to me would be a nightmare in some of the ways I used to work, that was a big time saver in this endeavor. Something that Ashley noted was what we did would have been 6 other programs. So 6 other tools or programs would have been used to do the same assessment. So that's a big one for me. So just I want to take just a couple minutes. I can show a bit of the model just briefly. All right, so here is kind of a close-up of the LID phase, we call it. Okay, so we're in, this is XPDRAINAGE, the software. You'll see in this tree view on the left, we have these different phases. Okay, so I have existing developed LID. Here's my LID phase. I can select this facility and look at, yeah, this is my rain garden, and modify these items if I wanted to. Okay, so that's what we're looking at. Rain garden. We have flow in to this rain garden. Okay, and there's a high flow bypass for the higher vents, bypassed out into this manhole vault and into the collection system. Something I can show. I might just jump to, let's say, the very early developed scenario. So here's a plan of what the site layout. You can see how early it is. There's even marker arrows showing where the flow is going to move. You can incorporate the surface, and that's how we actually delineate some of these catchments. All right, so just looking at this plan, let's size all these pipes. That's just one thing we did. I can show that pretty quickly. So I might add in a flow path. So the main trunk line will go from there to there. And we'll see that here's that purple main line, and here's all the laterals off of that. So for example, I could open up this, is our connections form, if you will. And it's going to list I chose this flow path. Here is that main flow path, and here's kind of all the laterals. We can size all this by checking the auto size option. You'll see here we have our flow rates that would be expected based on the rational catchments, ultimate capacity of the pipes, so on and so forth. Diameter of these pipes, you get the idea. All right, so we did that. Obviously, it takes just a second for both that developed scenario, for the green scenario early on. So something else we could look at would be just to kind of show, I think it's interesting, we'll see how all of these, the true drainage paths, the true layouts, are shown, are represented. We can show right in here how we have our, maybe there's a bit of a wall here in between our rain garden, spills over into our facility. And I like to just show how things could be resized. So for instance, if I want to change this facility, so I've talked a lot about changing the plan view. Okay, well, what if I wanted to, it's not going to be a 1 to 2 slope. We're going to mow this. I want this to be a 1 to 4 slope. We can mow this easily. So this little radio button here in the Dimensions tab, that's what will be calculated. So there's 2 inputs, and the third will be automated for us. So maybe I'll say, automate the calculation of the top footprint. Here's the base footprint. And let's make this 1 to 4 slope. You'll see this top area increased. So if I apply that to the plan, you'll see this area got much bigger. Okay. I could even adjust this view. Perhaps I will replace this outline. Like I say, it's not going to be a square. I want to show this to the client looking a little more rain garden-y. You get the idea, right? So I can do that, and all of the top area, the footprint, the levels, all of that has been adjusted based on what I've drawn. Okay. So we've already covered a lot of ground, spent a lot of time on this. The focus of this was just to cover what we have done in this preliminary case study. I would be happy to speak further on some of this, especially if individuals want to know more. Often a lot of individual questions on items like this. If there's enough interest, perhaps we look further at some of these items and maybe a following webinar or even just individual discussions. All right, so that's what I wanted to cover today. Again, I wanted to call out that this wasn't just something I myself put together. This was a lot of work from Ashley Francis and LJA Engineering on this case study, and a lot of this work that was presented at both the CESWA, you could think of EPA 4 regional conference as well as the EPA 6 regional conference. So Ashley was a great help, did a lot of this work. XPDRAINAGE, what we were talking about, what I just showed you, can be trialed. It's available for purchase. Just go to our website. Nicole mentioned the email address before, amsales@xpsolutions.com. Well, thanks everyone for joining, and thank you very much.